All right, so you should be seeing my screen here. And so the first question we had was a question on number 12. Okay, so in a crystal salt, there are electrons and positive ions. How does the net charge of electrons compare with the net charge of the ions? So let's see. So our options here. So in looking at this, this is kind of a poorly worded question. So you've got your electrons, which are negative. It says that you have positive ions, which would suggest that you have some of the items have lost their negatives, giving us a positive. So the fact that they are using, let's see, how does the net charge of electrons compare to the net charge of the ions? So what should happen, the way it's worded, I do believe, is so you've got electrons and you've got the positive ions. The positive ions are your protons, so they don't really give us much more. I'm thinking that in your salt crystal, what should happen is you should have something that is entirely neutral, which means that your number of electrons and your number of positive ions should end up canceling out. So how does the net charge of the electrons compare with the net charge of the ions? They kind of need to give us more. So, and when I was kind of going through picking questions, I don't know why I didn't eliminate this question, because it's not worded great. If it's neutral, if the salt crystal is neutral, that means your positive and negatives would cancel out. If you had, it says that you have positive ions. If that's implying that the salt crystals overall are positive, that means that your positive ions are going to have more charge than your negatives. So I don't like that question, and I don't know why I would have had that on there. So I'm going to put a little note to self there to delete that one. But hopefully the explanation about what your possible answers could be makes sense. Question number 24. We have a solid conducting sphere given a positive charge Q. How is the charge Q distributed in or on the sphere? All right, solid conducting sphere. To give it a positive charge, that means you've actually taken away some of the negatives. So we've got this object that has lost some negatives. Now what's going to happen is, because it says that it is a conducting sphere, since it is a conductor, all of the electrons, or at least the valence electrons, are able to shift and move very easily, which means that all electrons there are going to repel each other. So any electrons you have on the object are going to spread out as much as possible. So number one, that means it's going to be on the surface, because if I have any charge on the inside, they're going to push away. So you're always going to have charge on the surface of a conductor. You'll never have it throughout the body, at least the excess charge. So the few electrons that I have left, they're all going to repel away. They're all going to be on the surface, and they're going to push away from each other. And as they get further and further away, the force pushing them away gets smaller, which means that they're going to spread out evenly, because if I take any two electrons and somehow make them get closer, the force of repulsion is going to be extra strong. It's going to push right back away. And so what we're going to find is that it is on the surface. And since it is a conductor, and we're not told that it is polarized, that means that the charge will be equally distributed throughout the surface. So my questions here, my answer order is going to be different from everybody else's. Its density increases radially outward. No, there's going to be no net charge on the inside. The inside is going to be neutral. It's concentrated at the center. No. Answer 3, the density decreases radially. No. Is uniformly distributed throughout. No. 5, it is uniformly distributed only on the surface. So for me, answer number 5, because those charges are going to repel away and they're going to be found on the surface. There's a much more in-depth answer that we do when we start getting into AP physics stuff next year, in terms of the charge residing on the surface, but that's not for us today, not for us this year. That was question number 24. I had a question on number 33 and then 35, and then any others as well. Can an object be charged negatively with the help of a positively charged object? So one of the, let's see here, I don't know if, let's see, I want that right there. So what we had in our in the notes that we had done, we had charging methods. And so some of those charging methods included conductors, some included insulators, different methods. And so here we go. So now you should see it. And so if we go through, I didn't want to do that, fat fingers. So if we get down to, boom, right there. Charge by induction. Charge by induction is where you take a conductor, and I'm going to shrink this down a little bit so we can actually see what's happening there. So we take, using my cursor here, so what we're going to do is you're going to take some kind of a conductor. So right here, here's my conductor. Those red negatives can be shifted around anywhere. And we're going to bring in any outside charge. So if I bring in an outside charge, like here, it's a negative. And I can go through, and so what's going to happen, this negative is going to repel the red negatives over here. It's neutral but polarized. I can then use a ground, which is this symbol that's kind of cut off right there. You can see this symbol. That ground is low energy. It allows those negatives to spread out. So what's going to happen is these negatives are going to flow into the ground, leaving this as a positive. So what did I just do? I just used a negative to make something positively charged. If I look over here, I've got two objects held close together, and the negatives shift all the way over here to the left-hand side. I physically separate them. Instead of grounding, I physically separate them. I strand all of these red charges here, and now I've got a negative and a positive. I could do all of this if I had a big positive charge right here. I would just find that my negatives shift over here instead. And I can ground one side, and I can either remove electrons or I can add electrons. So if I go back to, I know you can't see it right this second, I'm just going to read it to you. It says, can an object be charged negatively with the help of a positively charged object? And the answer is going to be yes. And so let's see what our options are. So let's do this, 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 and back to that. So our options: yes, by bringing the positively charged object near the object to be charged and then discharging the far side. Okay, we'll look at that one possibly. Yes, rubbing two objects together. That's going to be, that's not going to do what we want to do. Let's see here. Yes, by bringing the positively charged and touching the near side. So it looks like for me, option 1 or 3, because it's yes, it's polarizing, and it's touching one side or the other. So we'll draw this one out here. Number 4, no negative charges can, nope. Letting two objects touch each other. If they both touch each other, they're going to share the charge, and so you end up with positive and positive. So it's going to be 1 or 3. So we're going to draw a picture and figure out how it is we would, let's see, we want to make an object negative. Okay, I want to make an object negative. So I'm going to do my best with this terrible little drawing feature. Let's give it a try here. So I need a positive, and then again, I'm trying to draw with a mouse here, so it's not the best thing here, but here is a big positive. Here is my conductor that is nearby. Come on, work. I'm frozen. There we go. All right, sorry, it's like a little glitchy and just my whatever. This is a nice piece of metal here. And so what I'm gonna have, come on. All right, let's not use the mouse because it's being a problem. So I'm just gonna draw a couple plus signs here, just enough to get the point across. This should look similar to what we just looked at on the smart file. So I got 3 plus signs, I need 3 minus signs. This positive source, this positive thing that's going to help me charge up, is going to, here we go, it's going to pull all these negatives to the left because opposites attract. So now I get this this neutral but polarized object. It's neutral, but the left side looks like it is a negative, and the right side looks like it's positive. And so what I'm going to do is I'm going to ground it. I'm going to touch one of these to the ground, probably by using a wire. If I connect over here, my ground is connecting to, my ground is connecting to something that appears to be positive. So a positive is going to attract negatives. This right here is an abundance of negatives that are not held all that strongly because it's the ground. It's got a ton of negatives, enough to match up with all the positives. So basically, this positive, okay, that wasn't supposed to draw right there, whatever. This positive end is going to be attracting the negatives that we have here. And so we're going to end up with some extra negatives flowing on to our item. This is charged by induction. If we would have touched this side, we would have allowed those negatives to continue moving a little bit closer towards that positive. They would have been pushed off onto the ground, and we could have made this thing positively charged. It all depends on which side you touch. And the only way to really do that would be to draw yourself a picture so you can see where those negatives would be found. So that was question number 33, involving induction and involving the ground. So it looks like we bring in the positive and touch the far side. Looks like the option that we're going to want to go with. And then there was a question on number 35, and then we'll reassess which questions we want to look at here. So it looks like question 35 is one of the big ones here where we have lots of steps. So I don't think I can. Yeah, I can't draw on this page, but you can see it. So I'll use my cursor and we'll try and take care of this one. So 35, what we're trying to do is we're trying to figure out the charge of both of them. So I'm not even going to read through all these. I've got neutral, I've got positive, and I've got negative. So basically, I'm looking for the charge of each of these when we're all said and done. So this is what I've got. I've got two things. It says they're uncharged, and they are, it says they're standing on a glass rod. That just means that they are isolated from the actual ground. So Y is up here in the air, and so is X. And they are touching. They behave like one ginormous conductor because that's how conductors behave when they are in contact with each other. A third ball with a negative charge is brought near the first here. So here comes my negative. And so what I'm going to have is I'm going to have all my extra negatives over here. All of Y's extra negatives and all of X's. Let me rephrase it. I said extra. They're not extra. The loosely held electrons, the valence electrons, the outermost electrons, because all of our conductors have electrons that are held really close to the nucleus, and those can't move, but the outermost can. So again, starting over, because I don't like my choice of words, the outermost electrons for Y and the outermost electrons for X all are going to be repelled to this side. I'm going to get a bunch of negatives built up here, kind of like the picture that I just showed you from our notes file. It was just reversed mirror images. I had these two things over on the other side. So all the negatives are built up over here. While the positions of these are fixed, the X is connected to the ground. So all the negatives here connected to the ground. So those negatives are going to flow off together. And the XY combo, because that's exactly what they are. They're a combination. They're a team. They're stuck. They're touching. They have both just become overall positive because the negatives that we had got pushed here and then they got pulled off. So basically, long story short, these two things have lost negatives as a system. They're positive. It says number 4, then the ground wire is disconnected. So while this is still here and then you disconnect this wire, these things are stuck as positives. Scrolling up. While X and Y remain in touch, the ball carrying the negative charge is removed. So these two things are still in contact. This thing has been removed. So they are still without negatives. They are still positive. By removing this, all you've done is allowed any charges that are left over to evenly distribute. I probably had, because this was a negative, this was probably a little bit more positive, this is probably a little less positive. Now they're equal. They're both lacking electrons. You then separate them. They're still both lacking electrons, which means that both of them should be positively charged. Because, going back to the beginning, they lost all those extra electrons right here in step number 3. And we never gave them a way to get the negatives back. The fact that we left them touching while removing our negative source out here simply means that whatever charge it has is going to be shared evenly. And we said it's going to be a positive charge, so they'll both be positive. And again, that's one of those where if you don't see it because it's kind of new material to us, you draw a picture. You show those positives locked in place, you show the negatives being pushed around, and then what does that ground do? That ground is going to make whatever it's touching, it's going to make it neutral. So if my ground touches a big negative thing, it's going to pull those negatives away. If it touches a big positive thing, it's going to give negatives. That's essentially what a ground does. It makes charged locations, not objects, but locations. It makes charged locations neutral. I can't believe how sunny it is outside.
These are just 2 questions about the PHET lab.
Yep.
So the first PHET lab, question 1, what charge method occurs when the foot slides across the carpet? Is it charged by conduction or charged by friction?
That's going to be friction because the carpet is an insulator. The shoe is an insulator, and so as it scuffs across, you got 2 different materials passing past each other. One's a donor, one's a recipient, so what's happening is charges are transferred. Once those charges get into your feet, you are a conductor, but the charge method was friction as the foot was going across the carpet. The charges got into your feet, and because you're a conductor, the charges start to transfer, and you have charge everywhere throughout your body.
Yeah, that makes sense. Okay, thank you. And the second one is on the PHET lab 2, number 6. Does the size of a neutral object relative to the charged object matter for rule number 4?
So did we see an example where a small neutral was attracted to a bigger object that had charge? The answer would be yes. We had the straw through our hair, the little bits of paper, and we saw an attraction, rule 4. Did we also see an example where the smaller object was the charge? And that would be yes. Take a balloon, rub it through your hair, stick it to the wall, stick it to the ceiling. So it doesn't matter which object is the more massive, the larger object doesn't matter. So I can have a small charge attract a big neutral, rule 4. I can have a big charge and a small neutral attract, and it's still rule number 4. So it doesn't matter which object has the charge, the big or the small. Newton's third law, they're both going to be attracted. So rule number 4 will always apply to any kind of a charge neutral scenario.
Okay, thank you.
Mm-hmm. I have to double check, but I know that a few people answered the little mini lab question about the rolling soda can, and Katie did a good job of getting us started with talking about the charged balloon. And then we had Rishi and Emily come back and say, I think it's because the can it's neutral, and a neutral will attract a charge. So the can, neutral, the balloon, charge are attracting each other. And then Emily went so far as to say, well, that can is a conductor, so we get a really, really good polarization, even more of an effect, which is an excellent answer. So that can, do I have a can sitting around here? I don't think I do. I must have taken it to the kitchen. So that can is going to have an extreme polarization because it is a conductor. So Emily answered that very well with, once those electrons have shifted one way, you get an extreme attraction between the remaining positives. And as the thing rolls, those negatives keep on being repelled to the far side, leaving the positives closer with a stronger attraction. So that was good on the Google Classroom if you checked out the comments section.